Welcome to this explainer. We're jumping right in to level up your circuit analysis skills by mastering the ultimate gatekeeper, the diode. If you've ever stared at a schematic and wanted a faster, more intuitive way to solve for these little directional components, well, you're in exactly the right place. We're going to break down the math, the logic, and the tricks to solving these circuits with absolute confidence. Let's get to it.
So think of diodes as stubborn toll booth operators on a highway of electrons. Unlike resistors, which just kind of smoothly slow traffic down based on Ohm's law, a diode makes a hard demand. If you approach it from the right direction and pay the toll, it lets you through. Approach from the wrong direction or just show up without enough voltage to pay, the gate stays shut. Traffic stops completely. Before we tackle our first actual circuit, let's just quickly lock in the three essential variables we're solving for today. We've got ID, which is the current actually flowing through our diode, then VD, the voltage dropped across the diode itself, remember, that's our toll, and finally VR, the remaining voltage across our resistor. Keeping these three straight, that's your key to unlocking literally every circuit we're going to look at. All right, take a standard silicon diode in forward bias. It demands a 0.7 volt toll. If our battery's pushing out 8 volts, we pay that toll no problem. That leaves exactly 7.3 volts left over to drop across our 2.2 kiloohm resistor. Divide that 7.3 volts by 2.2 kiloohms and boom, we get a nice 3.32 milliamp current flowing. But if you flip that diode around into reverse bias, it stops acting like a toll booth and turns into a massive brick wall. Current drops to absolute zero, no math needed there, the gate is totally shut.
But hey, that brings up a really fascinating edge case. What happens if the diode is facing the right way, but the battery just doesn't have enough juice to pay that 0.7 volt toll? Say we only have 0.5 volts to work with. Well, even though the diode is technically in forward bias, meaning it's facing the correct way, that 0.5 volt source falls short. Because we simply can't pay the toll, the gate stays completely closed. Our current remains at absolute zero, which means the voltage dropping across our resistor is 0 too. The diode essentially just sits there, absorbing that entire 0.5 volts of pressure, just waiting for a stronger battery to push through. Okay, let's take things to the next level. Let's test your intuition on what happens when diodes dual. Imagine a single closed loop, a powerful battery, but two diodes placed in series pointing directly away from each other. Who wins? The answer? Nobody wins. Honestly, it doesn't matter how much voltage you have pumping through that loop, even a really healthy 10 volts. Because they're facing opposite directions, one diode is absolutely guaranteed to be in reverse bias. It acts as a complete open circuit, entirely choking the source and keeping the whole circuit dead. Current is zero, voltage across the resistor is zero. It's a classic trick question you'll definitely see on an exam.
Things get a little more interesting when we add a second voltage source to the mix. With a 10-volt source pushing from one side and a negative 5-volt source pulling on the other, we actually create a total pressure difference of 15 volts across the entire line. By just subtracting our 0.7-volt silicon toll from that 15-volt total, we're left with exactly 14.3 volts of pushing power. Divide that by our total series resistance of 6.9 kiloohms, and we easily find our final current, 2.07 milliamps. The logic scales perfectly no matter how many batteries you throw at it. Now the whole rhythm changes when circuits split into parallel branches. If we take a 10-volt source and place two identical silicon diodes side by side, our main current loop subtracts the standard 0.7-volt drop, leaving 9.3 volts across the 4.7 kiloohm resistor. That gives us a total current of 1.98 milliamps. But here's the cool part. Because those parallel diodes are identical twins, they perfectly share the load. They split that total current right down the middle, meaning the current through each individual diode branch is exactly 0.99 milliamps. But the rules of the game change entirely when we start mixing materials. Up to now, we've only been using silicon, which demands that 0.7 volts. But enter germanium. Germanium is a cheaper toll booth. It only asks for a 0.3 volt drop. So what on earth happens when these two set up shop right next to each other? This right here perfectly illustrates the concept of circuit greed. When you put a silicon and germanium diode in parallel, electrons are lazy. They will always take the easiest path. The germanium diode essentially locks the node's voltage drop at just 0.3 volts. And because the silicon diode needs 0.7 just to wake up, it gets completely starved of pressure. As the math shows, the germanium diode hogs literally all the current at 2.06 milliamps, leaving the silicon diode completely off, zero current flowing through it whatsoever. We can actually combine everything we've learned so far to tackle some pretty gnarly series parallel circuits. Say we start with a 10-volt source. The current first pays a 0.7-volt toll at the top series silicon diode. Then it hits a node, where the path splits. The branch on the right goes straight to another silicon diode, demanding another 0.7-volt drop. By methodically deducting our tolls across these branches, we just apply Kirchhoff's laws. First, we find our main loop current is 1.83 milliamps. Next, the current branching down through the parallel resistor is 0.32 milliamps. Finally, we just subtract that branch current from the main loop, giving us a final remaining current through that second diode of exactly 1.51 milliamps. Just take it step by step, and these complex networks really do unravel easily.
Okay, time for the final boss battle of circuit analysis, ideal diodes. Ideal diodes are purely theoretical. They have a 0-volt toll in forward bias, and they act as absolutely perfect blockers in reverse. Now, in a complex multi-node circuit, we usually don't instantly know which way the current will flow, so we have to initially assume both diodes are conducting like plain old wires, and then do the math to see if our results actually make sense. Basically, we're checking if our calculated currents are positive. In this specific scenario, our assumption works out perfectly, giving us valid, positive currents of 1 milliamp.
To avoid falling into a massive engineering trap when solving these, you always want to follow a simple 4-step hypothesis testing procedure. Step 1, assume they conduct. Step 2, calculate the currents. Step 3, check for any impossible negative values. And step 4, if you find a negative, you assumed wrong and you've got to completely redraw the circuit with that specific diode turned off. Let's see exactly how that trap springs in action. If we assume both diodes conduct here, we do the node math and discover that the current flowing down through the first diode is an impossible negative 1 milliamp. Now, current simply cannot flow backward through an ideal forward diode. So this proves our initial assumption dead wrong, forcing us to recalculate with that first diode correctly modeled as an open switch. When we do that redrawing, we find the true current for the second diode is actually 1.33 milliamps. Always check your assumptions. And just like that, you've leveled up your understanding of basic diode gates. You're smoothly navigating forward bias, reverse bias, multi-source loops, and even those sneaky ideal diode assumptions. But I'm going to leave you to ponder this. How do these strict one-way toll booths behave when the voltage isn't coming from a steady battery, but an AC source that is constantly waving back and forth? That entirely changes the rhythm of the highway. Thanks for joining me on this explainer, and keep questioning how the current flows.